Good morning and afternoon, depending on where you are. We are about 2 minutes away from starting today's webinar with Highview Power and the Long Duration Energy Storage Association of California. Hello and welcome to today's webinar with Highview Power and the Long Duration Energy Storage Association of California. The webinar, A Clean, Reliable Electricity System at the Lowest Cost, will compare liquid air long duration energy storage to short duration energy storage. My name is Wendy Prabhu and I will be the facilitator for today's session. Just a few housekeeping items. All attendees are on mute to make sure everybody can hear the presenter clearly. There is also a questions panel on your toolbar. You can use that to add any questions you have during today's presentation. We will answer all relevant questions as we go through the presentation. We will not answer relevant questions as we go through the presentation. We will hold a short Q&A session at the end of the webinar. We are recording this webinar and we'll send out a link to all registrants at the end. And with that said, today's host is Julia Prochnik, Executive Director of the Long Duration Energy Storage Association of California. And our presenter is Richard Riley, Project Development Director at Highview Power. Julia, the floor is yours.
Thank you, Wendy, so much. And good morning and good afternoon to everyone. We really appreciate you taking the time to join us today to learn more about Highview Power and Long Duration Energy Storage Association of California. And I also just want to say personal thanks to Wendy and Sam and Kelly and Richard and Sal and Bonnie just for all working behind the scenes to pull us together. So thanks again for taking the time. So about the Long Duration Energy Storage Association of California, we're new and we're a group of supporters, organizations, businesses, and individuals to really serve to promote the development of long duration energy storage, to complement short duration energy storage, and to enhance California's ability to achieve its climate goals while operating a safe, reliable, and resilient energy grid. As you notice, our supporters are Blattner Energy, Cupertino, GE Renewable Energy, Highview Power, Nat Energy, NextEra Energy, Nextracker, McMillan Jacobs Associates, and Santec. And we really are grateful for Highview Power to take the time today to really start the initiative of launching our webinar series to learn more about the importance of long duration energy storage and the variety of new and emerging and existing technologies that are available. Highview Power is a long duration energy storage company specializing in liquid air energy storage. They are currently developing commercial plants in the UK and the United States. And today we'll hear a lot more from Richard, who brings a ton of experience as an engineer and recently, bringing Highview Power, opening up their offices in New York, and really focusing on the development of the new technology, liquid air energy storage. Many of you know me. I've been in the industry for over 20 years, working at the North American Electric Reliability Corporation, the U.S. Department of Energy, and recently as an advocate and joining as the new ED for long duration energy storage, which is really important, and I'm really excited to be part of this organization to promote the education of how we can meet California's climate goals and be part of the solution. So here's our contact information. Look forward to hearing more from you. Again, this is just the beginning of a series of webinars to promote the value add of long duration energy storage and the partnerships ahead. Our contact information is here, and look forward to a great presentation from Richard, your questions, and more dialogue. Richard, I'll hand it over to you, and thanks again.
Thank you, Julia. So I apologize if you hear train horns in the background. I'm currently on lockdown still, so there may be some background noise. So Highview Power, as Julia mentioned, is a designer and developer of long duration energy storage facilities. And we have spent the last 15 years developing and commercializing a long duration energy storage technology that utilizes liquefied air as the storage medium. So today I'm going to give a quick introduction into the technology, and then I want to talk about one of the key aspects that drives the long duration sort of value in the grid, which is grid reliability. And then I'm going to move on to a case study for a US utility that we've recently undertaken that attempts to tie together the multiple functions of energy storage in the network, including reliability and energy, and to evaluate a holistic, on a holistic basis, lowest cost portfolio of energy storage comprising both short duration and long duration. And I think it highlights some interesting dynamics, and I guess provides one way of distinguishing between what a long duration and a short duration system is. So regarding the technology, so this is really just to set the scene and sort of place the technology in the spectrum. So we have been developing liquid air energy storage for 15 years, and our fundamental philosophy is to utilize proven components and processes from adjacent industries so that we can rely on fully established supply chains, warranty arrangements, and what have you. So the technology itself is founded upon the same processes used in industrial gas and power generation. And so a liquid air energy storage system basically is a composition of pipework, heat exchangers, rotating machinery, and tanks. And that composition, the dynamics of that composition, makes this technology particularly well suited to high power and long duration applications, by which I mean greater than 50 megawatts and greater than 4 hours of duration. And the economies of scale that you find in the kind of rotating equipment that we use for our power systems means that the larger that we build the system, the more cost efficient it is in terms of dollars per kilowatt. And then in the duration axis, we achieve longer duration by building a higher volume of tankage to store liquid air. And that's a low cost thing to do. So we can very cost effectively arrive at the tens of hours of duration by expanding our tank volume. And so we end up with a system that really straddles the gap between the 4-hour lithium ion systems that we've seen deployed in very large numbers in recent times, and the very large energy storage systems like pumped hydro and compressed air, which in themselves can be very cost effective, but very large scale, and obviously require specific geographical requirements in order to be deployed. By contrast, we have a system that can sit in a relatively small packet of land above ground and be flexibly located, and as a consequence, more easily developed. So this is what a liquid air energy storage system looks like. So the render on the left is the 50 megawatt modular system that has been released for construction in the United Kingdom, and with which we have multiple projects in the US in late stage development. So it's a 50 megawatt standardized module, and the duration of the system, or the energy capacity of the system, is dictated by the volume of tankage attached to that power module. So in the render, you can see a 400 megawatt hour system. So this is a 50 megawatt 8-hour system. And that system occupies a packet of land of about 4 acres. So it's very compact, and we'll go into some of the additional benefits of the technology in a later slide. This system is really building on the experience that we've derived from the two systems on the right. So the first being a pilot system that was the first fully integrated liquid air energy storage system in the world, built and operated by Highview, and then latterly a demonstration system of a 5 megawatt scale that has been used to demonstrate the provision of real grid services in the UK national grid, so providing operating reserves, frequency response, and also some services that are still under definition in the UK, such as inertial response, remunerated reactive power response, and then fast frequency response as well. So how the system work, as I mentioned, we're repurposing processes that already operate in other industries. So the first part of the system is an industrial air liquefier. So this is basically a large compressor-loaded refrigeration system that draws in ambient air and cools it down until it becomes a liquid. And this is a system that's used, it's based on the Claude cycle. It's over 100 years old and has been used as the predominant way of producing liquid air to then produce component gases, nitrogen and oxygen. So we're taking in air, we're running a set of compressors, we're compressing it, we're cooling it, and then we're expanding it back down to a low pressure, at which point it condenses into a liquid state. And so that liquid air is in the same proportions as ambient air. It's 700 times denser, so it can be stored in a reasonably small space. And most importantly, it's at low pressure. So we're able to store that liquid air in steel tanks that can be constructed above ground without the expense of containing high pressure. And those tanks essentially resemble large thermos flasks. So they're very well thermally insulated. They're designed to contain a moderate pressure of about 15 atmospheres. And the liquid air will sit in those tanks for many weeks and with minimal loss because the tanks are very well thermally insulated. When we want to recover energy from the system, we extract the liquid air from the tanks, we pump it up to high pressure, and then we reintroduce heat, and we end up with a high temperature, high pressure gas, which is very similar to steam, except that it's dry air, which is one of the most benign fluids that any system could use. That dry air is passed through a turbine. The turbine is a repurposed steam turbine, so it's a model that is operating in other processes using steam, and we have essentially procured it with slightly reworked internals to accommodate a slightly different process fluid. That is at the 50 megawatt scale an axial machine, so it looks very much like a steam turbine. And it is coupled to a synchronous generator, and it puts AC electrical energy back onto the grid. And that synchronicity is an important sort of additional value adder for this technology. So the synchronous system can provide real inertia, it can provide real dynamic reactive power, and a very high short circuit contribution. So we were able with this system to provide quite a lot of additional benefits to the grid in terms of supporting its stability and enabling renewables beyond just the real power benefit of an energy storage system. And so to close the system, we have thermal recycling within that process. So when we cool air to liquefy it, we're obviously extracting heat. We take that heat out, we store it in a thermal store, which is essentially, again, steel vessels. And we use that heat, we deliver it to the interstage reheat on the turbine, which is a 4-stage turbine. And we use that to recover additional energy from the system. So there's no combustion within this process, it's entirely self-contained, and we use heat internally derived from the process. And then similarly, when we take liquid air and we raise the pressure to ambient and beyond, we're extracting a lot of cold energy. We store that cold energy inside, again, steel tanks, this time containing a gravel medium, so rock, a packed bed of rock, which stores that cold, and later we extract that cold and we deliver it to the air liquefier to do some of the cooling on the charge system. So we end up with a process that's up to 60% efficient, and it's comprised of 3 entirely independent subsystems. So we have flexibility on sizing the charge system up or down so that we can charge faster or optimize CapEx depending on the requirement of the system. And similarly on the discharge. And then finally, the storage is the tankage in the middle holding thermal energy, heat, liquid air and cold. And expanding the duration of that system is the lowest cost component of the overall system. So that's just a case of building larger tanks or more tanks, and we can very efficiently build out the duration of the system. And we can also do that as a retrofit when to basically provide flexibility as grid needs evolve. We can add duration to the system. So overall, we end up with a system that is easily sited on a small footprint with no geographical constraints. So if you can build traditional industrial process on that land, like a power plant, you can build this system. We're using components that typically are designed for a life of 30 years. And as with any thermal generator comprising very similar equipment, you can expect to extend that duration by overhauling at 30 years certain items of equipment based on their condition. And it's not uncommon to see 40 years or more from those kind of systems. The process fluid and the fluids used to store heat and cold are fundamentally environmentally friendly. There's no emissions, there's no combustion, no effluents from this system. So essentially what it does is it takes in air from the atmosphere and it puts the air back out to the atmosphere in exactly the same composition. And then we're using a fundamentally non-combustible set of storage media to store our energy. And that means that we have very safe construct. There's no need for active safety systems to keep this process safe. So we have very low fire risk, and essentially if we lose power to the system, we can walk away from it, and there are no emerging issues from not being able to supply power the time it takes to restore that power. Okay, so that's a quick tour of the technology. Now, obviously, energy storage in general performs multiple functions in an electricity system. Today, we're going to consider 2 of them. The first being broadly characterized as energy. So the most intuitive justification for energy storage and the most intuitive reason for long duration energy storage is obviously looking at the increasingly long periods of time that we're going to need to cover when renewable energy is not available, but we still need to serve load. So if we assume a system like in California with a lot of solar and very little wind, we're looking at around 16 hours of the day where we're going to have to find solutions to plug that gap when the sun is not producing significant amounts of energy. So that's the energy justification. And the second aspect that I want to look at is reliability. And this is a big topic in California and elsewhere in the world. And arguably will be the first kind of consideration, or the most pressing consideration in the initial deployments of long duration energy storage. So historically, we've obviously had about 100 years or 150 years of power generation. Historically, it's been based on fossil fuels. So we've had systems that can provide essentially fully dispatchable generation. And we've become accustomed to a reliability that effectively equates to about 1 day of outage every 10 years. So this is all about, keeping the lights on and the expectation that those lights will be on with very, very high reliability. So 1 day of blackout every 10 years is really quite an impressive feat and testimony to the kind of planning and organization of utilities and the body of knowledge that's been built up over 100 years. And maintaining that reliability is a question of planning, and that planning happens over multiple timeframes. At the very short scale, it means deciding what is going to dispatch in the next hour or the next day, and then at the longer timeframes, it means deciding what generating capacity we're going to build to cover the next several years of need. And that's really the focus of this presentation. So in order to achieve that high reliability, load serving entities are required to maintain enough generating capacity to cover their peak load. And then they're required to maintain a sufficient margin in their generating capacity to cover unexpected events. Now, unexpected events could mean an error in the forecast of load from one day to the next, or an error in the forecast of load growth from one year to the next, or it could mean sudden loss of a very large power generator without unplanned outage that has to be covered by other resources in the stack. So clearly, a lot of things could happen that are not planned for. And in California, that margin for system installed capacity is dictated or defined as 15% of peak load. So broadly speaking, a system is deemed to have adequate resources or resource adequacy if it maintains 115% of its projected peak load. Now, this question becomes more complex when you consider energy storage. So clearly, many decades of experience have proven that 15% margin is adequate to maintain reliability. But that has been proven on the basis of more or less dispatchable or completely dispatchable generation, so conventional generation, notwithstanding outages or fuel constraints, which do exist. If we consider a perfect conventional generator, it's basically available for as long as we need it, whenever we need it. Clearly, energy storage is not. By definition, it has a limitation on its duration. And so a 10-minute energy storage system, for example, will not be able to replace a conventional generator. And as we have longer and longer duration, we obviously approach the ideal case, which is unlimited generation. So while a conventional generator can provide, let's say for idealized terms, unlimited generation, it doesn't need to be able to do that. It needs to be able to provide enough power for long enough. And the big question in all the power grids today is how long is long enough to provide firm capacity? And the undisputable fact is that it is linked to the duration of the system. It's just a question of how long, at what point we arrive at full firm capacity. And the way that is typically measured is to evaluate the loss of load that would be expected with a perfect generator, and then to look at energy storage of a particular duration and say, okay, in comparison, how much load is lost, and from that you can derive a firm capacity equivalency, which is often known as capacity value of your energy storage system. So from here, I'm going to dive into a case study, which I hope will provide a better illustration and hopefully tie some of these concepts together. And what we've essentially done, we've worked with a utility in the United States, reasonably small utility with 5 gigawatts of load, vertically integrated. And they are building out significant amounts of solar over the next 5 years. And they're also retiring conventional generation. So they find themselves in need of about 200 megawatts of additional capacity in order to cover the reserve margin that they're obliged to hold. And so we set out to work with them to look at a portfolio of long and short duration energy storage and to understand what an optimum mix might look like to respond to that need. So the objective essentially is to provide the lowest cost for 200 megawatts of firm capacity while maintaining equal reliability to the present situation. And an important factor is that they don't want to rely on imports in order to cover or provide reliability, because doing so amounts essentially to relying on a neighboring grid that may not be as aggressively decarbonizing as the system that we're looking at. So importing from a less decarbonized grid is treated in this analysis as a last resort. And the metric that we're using here is the net cost of firm capacity, which I'll look at in more detail. So this is how we evaluated the system. So we established a baseline based on the generation that already is going to exist in 2025. We produced a production cost model that incorporates the cost of generation, cost of starts and fuel, and everything that's needed to produce a production cost. And then we evaluated individually different options for energy storage within that system. So we took the predominant short duration technology, which is lithium ion, and we defined 5 system options using lithium ion, so 2, 4, 6, and 8 and 10 hours of duration. And then we did the same with liquid air energy storage, which obviously we define as a long duration system, but ultimately we're treating them both as the same on the same basis here. And we'll see in later slides how the dynamics of the two technologies are quite different. So we take the baseline, we evaluate the system option, the storage system in that baseline for both its contribution to reliability and its benefit in terms of minimizing the production cost of the system, which means dispatching solar energy essentially into the peak hours and avoiding things like system starts and what have you on inflexible thermal generation. And so we figure out what is the lowest cost option. We integrate that lowest cost option and we establish a new baseline, and then we evaluate the next option in the system. The metric that we use to compare is the net cost of firm capacity. So we take the gross cost of the system on an annualized basis, so the cost to cover CapEx and OpEx. We then evaluate that system in the production cost model and determine the benefit to the production cost, and we net that benefit off the overall cost of the system. And the remaining cost is the net cost of the system. And we normalize that by the kilowatts of firm capacity that energy storage system can claim in this utilities system. And so another key component is the firm capacity calculation. So what we've done is we've compared the loss of load expectation. We've used an effective load carrying capability method. And we've evaluated the storage options against a perfectly dispatchable conventional alternative and determined a firm capacity equivalency as a function of duration. And we've done that individually for each technology. And we found that actually the technologies are very, very close. So we have incorporated a capacity value, essentially a firm capacity value for each individual technology, but they're very close to each other. And what we find is that we need between 8 and 10 hours to provide the reliability of a conventional generator in that system. And the curve that you see there is for a system that currently has no energy storage, and we're looking at deploying the first 50 megawatts of that 200 megawatt stack. And as we deploy more and more energy storage, that curve trends downwards, and we need longer durations. And that will become apparent in the results. So on the subject of duration, I mean, this is a hot topic in California. It's a hot topic elsewhere in the US. There's a lot of discussion around what constitutes firm capacity. And it is a function of the network. It's a function of the penetration of renewables. It's a function of penetration of storage. And the important thing is to understand and evaluate that and to fully quantify it within any energy storage evaluation. So here we're looking at a situation where we have no energy storage yet deployed in this system. And the thing that you'll notice, so we have the short duration option, which is lithium ion, and the long duration option, liquid air energy storage. You'll notice that their cost of firm capacity plotted against duration has a fundamentally different shape. And so with the short duration option, essentially what we're looking at is the cost of building out that duration increases, or the effective cost of building out that duration increases as we increase the duration. So ultimately, the cost of building out the duration outweighs the benefit of that duration within this system. Conversely, the long duration energy storage system initially, because of the very low cost of building out duration, you can actually derive more benefit from that duration than you derive cost. So we find that the cost of firm capacity actually reduces as you build out the duration, and then we find an inflection point beyond which additional duration is less and less useful, and the cost starts to turn in the opposite direction. And ultimately what we find in this first tranche of energy storage in the stack is that we're looking at a system with quite a lot of opportunity for energy arbitrage. And so a technology like lithium ion, which is efficient and low cost for short duration, is able to provide greater value into the system by moving energy around. And it does provide some firm capacity contribution as well. So we find that it makes sense to build a shorter duration system in this case. But that situation evolves as we build more and more storage into the stack. So the next slide is a situation where we already have some storage deployed into the system. And so here we're looking at, we've already deployed 150 megawatts into the system. And the shape of the results looks very similar, but the lithium ion curve has moved upwards relative to the liquid air. And that's because we've used the most fruitful opportunities for arbitrage, and really reliability is starting to be the main driver of value in the system. And so we start to see another effect of that reliability becoming more important, and that is that the inflection point for the long duration system is starting to move to the right as more duration becomes more valuable. So looking at this on the basis of the whole stack, what we found in this particular system is that, and I think this is really a conclusion that is universal ultimately, that the most cost-effective capacity stack is ultimately going to require a mixture of technologies. In this case, we've looked at lithium ion and we've looked at liquid air as a short duration and long duration technology. And we find that we need between 50 and 100 megawatts of lithium ion, a relatively short duration. And then we become optimal with 100 and 150 megawatts of liquid air with longer duration. And obviously, this is an analysis, so we foresee that once you take into account project economics, there will be an area where both technologies probably compete well, and it will come down to project economics. But ultimately, eventually, you need to introduce longer duration if you want to maintain a reliable system. And so while the specifics of that statement depend on the system that you're looking at and the constraints on that system and the resource mix, I think that's fair to say that's a universal effect. So in conclusion, we see that ultimately you can actually compare multiple durations by looking holistically at the functions that energy storage provides in the network. So we have here considered production cost or energy and reliability. And we've been able to define a metric that allows us to look at a spectrum of durations and determine when long duration makes sense. And duration is closely tied to the reliability aspect of that value. So while in larger systems, obviously, there will be a greater potential for shorter duration systems to provide their value. Ultimately, as higher penetration exists, longer duration energy storage will be needed. And that effect is exacerbated in load pockets and smaller systems. So when you start to account for grid topology and local factors, you can see that effect is actually amplified. And a truly holistic evaluation will obviously include other sources of value that haven't been quantified here, like locational value within the system, T&D deferral, reactive power, inertia, and other features of various energy storage technologies that will become more important as we decarbonize to a greater and greater degree. But knowing that, you know, load pockets are going to be the area where this really it's starting to manifest already and show the value of long duration storage, that really highlights some of the benefits of liquid air energy storage, which is firstly, obviously, the low cost associated with longer duration, and then the flexibility of siting and the relatively small footprint that is required to put one of these systems down. And an additional benefit is the fact that we can be very flexible in how we manage our state of charge. There's no effect of degradation related to the state of charge of this system. So we can very flexibly manage that to provide the most value to the system. And it also means that we don't have to take mitigating measures to maintain the duration of the system. So if we build a system with 8 hours of storage, the system will maintain those 8 hours over the lifetime of the system. So that concludes my presentation. So I will yield to Wendy. I realize we have quite a long time now for questions. And Wendy, you can field them to me and I'll do my best to answer them.
That sounds great. Thank you, Richard. We do have quite a few questions, so we will try to get to all of them. If for some reason we are not able to address your question, we will send an email to you directly. But Richard, I will start with the first one. What is the efficiency of the system from AC in to AC out?
So the efficiency of the system is 60%. For the liquid air, and for the lithium ion, we've used an 85% efficiency for the equivalent AC to AC. And that obviously factors into the production cost benefit of each of those system options.
Great, thank you. There are studies that show that 4 hours is sufficient in California to provide full capacity value for some time. How does that relate to these results?
Yes, and I think that's it's not a settled question at the moment, and this is a topic of discussion across the US. Ultimately, here we're looking at a different system. We're looking at a smaller system, and we're looking at a system where explicitly imports from neighboring grids is not desirable, and that frames our calculation. But ultimately, this is a question that is being heavily explored, and it really is important to get that right if we're going to maintain reliability. The undisputable fact is that as you build out more and more storage and more renewables, eventually that long duration need emerges, and we see that it is emerging already in California and elsewhere. On a local level where you start to consider grid topology and local constraints.
Great. So what are the mediums that channel heat and cold? Both cold and heat have gravel in the tanks.
So the heat is actually recovered at 2 different temperatures. So there's a relatively low grade temperature recovered in a water glycol mixture and stored in a moderately pressurized hot water thermocline, very similar to what you see on combined heat and power. And then the higher temperature heat is stored in a molten salt solution, and that is used to extract even greater amounts of power from the power recovery discharge unit on the discharge. And then the cold energy is stored in a packed bed of gravel, very low cost energy storage medium. And all of these fluids or gravel and fluids are stored within steel tanks, thin walled steel vessels.
Great, thank you. Is there scope in the air liquefaction process to capture CO2 from the incoming air and dispose of the same?
Yep, I was asked that question just yesterday. It's a technical feasibility, but there's no economic justification to do it right now. I think ultimately it's the same debate as direct air capture to capturing CO2 at the stack, more efficient to do it where it's in higher concentration. And ultimately, we have a process that is aiming to maximize efficiency rather than extract CO2. So while it's possible, at the moment, we're not considering it because there's really no economic justification to do it. So ultimately, we take air in from the atmosphere, and then we put the exact same air back into the atmosphere.
Okay, great. So how do you ensure that storage is dispatched to maximize its capacity contribution?
That's a very good question, and this is something that we have undertaken analyses on, so sensitivities on, and there are various ways of looking at it. The way that we've looked at it is to define an average state of charge. Ultimately, in reality, there are likely to be periods where the dispatcher deems it necessary to maintain a higher state of charge, and times when they determine that it's possible to use their state of charge to provide better or greater production cost benefit. But in this analysis, we've assumed and we found that the sort of best assumption in terms of balancing production cost and capacity contribution is to assume an average state of charge of between 50 and 80%.
Perfect. This question's on inertia. Is inertia also delivered during the charging process?
It can be. So obviously the predominant, well, the first answer is yes. We have direct online compressors that are coupled synchronously to the grid, so they provide inertia. But ultimately, the true contribution of inertia, dynamic reactive power, short circuit contribution is derived from the synchronous generator. And so that is the piece of equipment that provides the most benefit to the system. And normally, of course, that would only provide benefit while the system is discharging. But we actually, for our UK project, have developed what we call the stability island. And this is because some of these services are actually remunerated in the UK, namely inertia. And what that introduces into the system is a clutch and a flywheel between the generator and the turbine expander. And that means that we can decouple the two, and we can operate that generator as a synchronous condenser with added inertia from the flywheel. And that will provide dynamic reactive power, real inertia, and short circuit contribution, regardless of what the operating mode of the system is. And at the cost of just a small amount of power drawn from the grid to turn that synchronous condenser.
Great. Now this question, do you have any thoughts to much longer term energy storage similar to the LNG model of, say, like 2 weeks of storage, maybe using larger membrane tanks?
It's absolutely feasible. At the moment, it's not our focus because the economics are around, I would say, broadly speaking, 4 to 10 hours. But it's absolutely feasible to look at 2 weeks of duration, yes.
Perfect. What is the ratio of the electricity taken from the grid to the electricity restored to the grid at the end of the storage process? I.e., what is the storage system's own electricity load?
So during the cycle, all of that is factored into the round trip efficiency. And then the only additional load of the system is the standby load, which basically covers mainly the control system and a few other balance of plant items. And that's measured in the hundreds of kilowatts. So it's about 300 to 400 kilowatts on top of the round trip efficiency.
Perfect. For the modeling, what weather did you use, and what was the penetration of solar and wind you assumed for the modeling?
So the penetration of solar is approximately 25%, and there's no wind on this system. It is a southerly location. I unfortunately can't say exactly where it is, but it's a southerly location with a fair amount of solar potential. approximately equivalent to California.
Perfect. What are the fundamental reasons behind the lower slope of the liquid air energy storage cost curve compared to lithium-ion cost curve?
So it's really a function of that cost of building out the duration. So it's the cost of an additional set of tanks or additional tank volume compared to the cost of additional packaged battery cells for the lithium ion.
Perfect. How much energy can you store per hour?
Also a very good question. So in this analysis, we're assuming that we are charging at the same rate as we're discharging. So we're pulling 50 megawatts off the grid at the same and discharging 50 megawatts onto the grid. That is actually a free variable, so we can build a larger liquefier and we can pull energy from the grid at a higher rate if required, or a lower rate if we can provide the value and minimize capex.
Perfect. And then can you tell me what the footprint is like compared to like a large another large lithium ion plant?
Absolutely, yeah. So it's roughly equivalent for about a 6-hour 50 megawatt system, but much in the same way as we derive cost benefits from economies of scale, there's a similar benefit in footprint. So as we build out to 10 hours and longer, the efficiency of the footprint actually significantly increases just by the proportion of the plant that is occupied by the storage tanks.
Okay, perfect. And then I think this is going to, well, no, we've got quite a few more. I'll throw some more at you if you're ready. What is the plant annual availability?
So we have a design standard. So we conduct our reliability, availability, maintainability studies to a standard of 97%. And then if the project requires, we can design a specific project to achieve the requirement. So just as in traditional power generation, it's a question of evaluating the system and the reliability of each component and providing the redundancy in the instrumentation and the key components that's required to achieve that.
Perfect, thanks, Richard. Is there any application of this technology to deal with seasonal load differences?
So it's a technically possible to consider, but similar response to the previous question about multiple weeks. At the moment, the market is in shorter duration. So I guess it's a question of watching how the economics pan out for seasonal storage.
Perfect, thank you. What is the time of the system and what is the startup time of the system and what is the ramp up speed?
So this is not an inverter-based technology, so it can't react immediately in the way that a battery would be able to, but it can react very quickly. So typically, the limiting factor is actually just how quickly we can ramp our cryogenic pump to deliver air into the turbine. And so we have actually two modes of operation. The first is we have everything completely static, and so the startup to full power is dictated by the time it takes to synchronize and then ramp to full power. And so that can, depending on whether the system operated the day before or maybe it's been idle for a week, is between 6 and 10 minutes. And then if we have the system synchronous and operating as a synchronous condenser, we've already sort of done the very precise operation of synchronizing the system. And so then for a warm system, we can ramp to full power within a minute. And then with a cold system, we would ramp the system within 5 minutes. So faster than a typical power plant, but longer than an inverter-based system. But obviously, you know, one of the things that we've looked at with our demonstration plant and we've installed on that plant is a hybridized option. So we have demonstrated the operation as a synchronous system and the ramping from a synchronous state, and hybridized with flywheels and supercapacitors to basically provide the best of both worlds. So we have a short duration, very fast reacting technology, and we operate the two together to provide very, very fast response, which in the UK is actually a remunerable service, and with the duration behind that very fast response as well. So there are architectures that can aim to provide very fast response if required.
Perfect. Thank you, Richard. I think we've got a couple more questions. How much wasted energy do you estimate that you can eliminate from renewable sources?
That's a very good question. It's not a metric that we've directly looked at here, or at least not one we've recorded. I mean, it really depends on the system, right? So it will be significantly different in a high wind system to a high solar system to somewhere in between, and you know, that really speaks to the balance between, or the relative importance in different systems of reliability and energy value in the system. So clearly on a high level, we are making good use of renewable energy that would be curtailed. And we actually do have a webinar that we delivered maybe 9 months ago, which we can certainly circulate the link again, where we looked at the New York grid and we asked that very question. So maybe you can get in touch and get a link to that webinar.
Perfect. And if anybody does have any questions, you can always reach out to us or additional questions or need links to additional webinars. You can always reach out to us at highviewpower@mercomcapital.com or reach out to Richard and Julia per the slide, and we can get those over to you. Go ahead.
We'd be more than happy on the long duration energy storage website to post the links to those previous webinars, because there's a great deal of expertise and knowledge there. So thanks for highlighting that, Richard.
Okay, Richard, this is the last question I'm going to ask is how flexible is the discharge equipment in terms of startup time, minimum stable generation, ramp rate, etc.? Is it comparable to a lithium-ion battery?
So I guess partially answered the startup time aspect of that question. In terms of how it can follow load, the system can operate right down to zero effective load, and ultimately the way that works is we have a turbine that has many of the same properties as a traditional generator, in that it has a minimum stable generation point, which depending on the specific equipment model is between 10 and 20%. And then we can, if necessary, dump energy within the system to basically trim that down to zero. And in some cases that's necessary to do, although it's an infrequent, it would be performed infrequently. So we can cover the full spectrum. When you think about how the efficiency response to that turn down, it's kind of similar to a heat rate, in that as you drop your power output, you will slightly lose some of your efficiency. But the difference between this system and a combustion system is that we're operating at very stable temperatures at the inlet to the turbine. So you have a very flat response, at least down to 50%, and that provides quite a lot of flexibility. We did actually perform a simulation using data provided by PGM in our pilot plant in the UK, and we did a load following exercise on the Reg D signal, and we performed a score of 97%, and the pass score is 97%, or at least it was. So we are very flexible in following load as well.
Perfect. Thank you, Richard. I just want to remind the audience, we did have quite a few questions here. So what we will do is we will, if your question was not answered, we will go ahead and send a response to you. I want to also thank everyone for coming to the webinar. We will have a recording of the webinar once it's done, and a link will be sent to everybody. And thank you both, Julia and Richard, for this presentation. If you have any more remaining questions, again, you can reach out to us at highviewpower@mercomcapital.com. And that's a wrap. Julia, did you want to add anything, or Richard?
Thank you, Wendy. This is Julia Prochnik, and I just want to thank again everybody for joining today, and wanted to remind that we'll put all this information on our website. We will be having additional webinars focusing on additional new and emerging technologies, and work with LBNL and UC Merced. And just really wanted to thank Richard and the Highview Power team for really sharing all of the depth of experience and expertise in promoting how long duration energy storage really does enhance the reliability of the grid and provide essential ancillary services. So thanks again, Richard and team, for a great job of what Highview Power is able to provide.
Yeah, and I'd just like to say thank you to everyone for listening and for asking some great questions.
Yeah, great questions.
Thank you. And that's the end.
Thank you.